Hello, everyone, and welcome to the Geoscience and Geoenergy webinar of 14th of April 2022. My name is Maartje Boon. I'm a colleague of Hadi, who is sitting next to me from TU Delft. And together we have the pleasure to co-host today's webinar. So we're delighted to host Catherine Peters from Princeton University as our distinguished speaker. So Catherine Peters is a professor of geosciences and geological engineering, chair of the Department of Civil and Environmental Engineering, and director of the undergraduate geological engineering program at Princeton University. She's an expert in environmental chemistry and geochemistry, known for her leadership in sustainable energy technologies. She is a fellow of the Association of Environmental Engineering and Sciences Professors and served as president in 2002. In 2020, she was awarded honorary board certification by eminence in AAEES and received a Distinguished Alumnus Award of CEE at Carnegie Mellon University. She's editor-in-chief of Environmental Engineering Science, and she earned her PhD in civil engineering from Carnegie Mellon University and her BSE in chemical engineering from the University of Michigan. She teaches courses in environmental chemistry, energy and the environment, and sustainable design. So thank you, Catherine, for graciously accepting our invitation. So to the audience, please note that this lecture will last for about 30 minutes, followed by questions. And please type your questions in the chat box, and then Hadi will take them after the lecture. And please do not wait till the end of the lecture to post your questions, but just type them whenever you feel appropriate, as your questions may trigger other questions by other participants. Catherine, we're very much looking forward to hearing your lecture, so please start whenever you're ready.
Thank you, Marta, and thank you, Hadi. Thank you very much for that introduction, and thank you for inviting me to be part of this webinar. Today, what I want to do is share with you some very promising strategies for decarbonization, and including carbon mineralization, carbon utilization, and sequestration. So I'll start by saying that we need to look underground for a climate solution, and I'll share some highlights of my research related to geologic sequestration of CO2. And some of this work dates back quite a few years. And I feel that over this time, my group has generated some important findings that tell a story about the reliability and safety about geologic sequestration of CO2. I'm also going to talk about some of our new work on carbon mineralization and utilization. And while I've been talking, I bet you've looked at this beautiful nano X-ray CT image. This is a synchrotron image, and it's an example of carbon mineralization. What you're seeing here is a vaterite particle, that's a calcium carbonate particle that has taken up arsenic with it, and that's why you see the different shades of gray in this image. And I have some slides on this to explain it further later. Okay, let me advance my slide here. There we go. Okay, so I want to start with a broad overview about negative emissions technologies. As you know, globally, atmospheric dioxide concentrations have risen to a level that we're starting to see and be very concerned about temperature rises in Earth's global temperature. And this is leading to risks about warming of cities, sea level rise, increased frequency and severity of storms, flooding, drought, wildfires. So it is widely agreed that massive decarbonization will be needed between now and the middle of this century. Greenhouse gases will need to be offset with negative emissions technologies. And so we have this acronym NET. NETs remove carbon from point sources or directly from the atmosphere and then utilize it or sequester it. Many of the roadmap analyses say that negative emissions technologies will play as significant a role as any of the low carbon technologies. And by 2050, NETs can account for as much as 10 gigatons per year of CO2 of negative emissions. So I'm going to, in the first part of my talk, I'm going to talk about geologic sequestration of CO2 and the research we have done on this. And I think many of you are familiar with this technology. Technologies exist to capture carbon from point sources and directly from the air. And after that capture, then CO2 can be injected deep underground, typically a kilometer or more, where it can be permanently stored. An example is the storage that's happening in the North Sea, right there where you are, with your location near Rotterdam and the North Sea. You're at the heart of one of the world's most important areas for geologic sequestration of carbon dioxide. Projects like the Trans-European CO2 transports project will be important in the coming years, and it's happening right there in your vicinity. In the United States, we've had mixed success with commercial scale projects, but we have had great success with research and demonstration projects. And the Department of Energy has now well-established protocols for operations, monitoring, and risk assessment to prepare for a CCS industry. So on this slide, this is my last broad interview slide. I show an image collection by the US Department of Energy, which they created a few years ago for their Subter initiative. The subsurface environment is a busy place, and that's what's shown here. And while historically we've thought about oil and gas extraction as being the way we think about subsurface energy resources, in the 21st century, the subsurface becomes a resource for negative emissions of carbon. And I think we will vastly expand the use of the subsurface to positively affect the climate, including sequestration of greenhouse gases. And here that's depicted by the word storage. So in the remaining, not in the remaining time, but in a few more slides, I'm going to comment on the research we've done on geologic sequestration, because in my opinion, this will be key to achieving climate goals by the middle of this century. So over the past 15 years, renewable energy from wind and solar has progressed faster than anyone would have predicted, but fossil fuels still dominate. According to the US Energy Information Administration, currently 60% of our electric power production comes from fossil fuels, and predictions are that this will not only continue, but may actually increase. So a means of taking care of that carbon is essential. All right, now let me focus a little bit on our work. The main research question that motivated us over the last few years is the question of, if you put CO2 underground, will it leak out? When I started this research, I thought about the enormous geochemical perturbation that comes from introducing vast quantities of CO2 underground. And I wondered whether acid would erode the overlying cap rocks, that might enable CO2 to leak from where it was injected. My PhD students and I looked at this from all angles over more than 15 years. And I'm jumping to the conclusion, but many papers and many PhD students later, I've concluded that it is highly unlikely for CO2 to leak from the target formation that it was injected into. In my opinion, geologic carbon sequestration is a technology that we can and should be doing reliably. What I'm showing on the slide on the right is this geochemical perturbation of the acidification that comes from CO2 contact with water under the high pressures you encounter a kilometer underground. And so let me tell you about some of the reasons I think that that's not a concern. Okay, here's a graphic from an experiment we did quite a few years ago. And sorry, I lost my cursor. This is an experiment that was novel at the time in that we had fractured cores and we were looking at the extent to which high pressure CO2 would erode the calcite that was in this rock. And this rock that for this experiment was a cap rock from a demonstration injection project in Michigan. And so it was typical of some of the cap rocks for CO2 sequestration projects. And what this experiment was novel at the time because we had the acid reactive flow through the fracture while the fracture was being imaged in 3D. This experiment was done at a novel facility in the United States called the National Energy Technology Laboratory, NETL. And so here's on the left of this slide that I've just clicked on, what you see is the result. The way we look at the results is we map the change in aperture of the fracture. And so the color you see in this aperture map on the right is showing where dissolution has occurred. So it's not a surprise that dissolution has occurred and the aperture has increased. But an important finding is how uneven those aperture changes are. For example, I hope you can see my cursor. There's an area here that's a clay-rich area that has not dissolved, and that serves as a bottleneck, a blockage in the direction of flow, and it will inhibit or end up controlling the permeability evolution. I then had a student who wanted to look at a simpler rock, simpler mineralogically, and she, Hang Dang, looked at Indiana limestone. And what we see is completely different in Indiana limestone. We see a channelization that forms, and that is as expected in a mineralogically pure rock, because in a mineralogically homogeneous rock, you get this positive feedback that leads to channelization. And then you think, oh, there's going to be runaway permeability evolution. But the truth is that the vast majority of rocks that are cap rocks are mineralogically very heterogeneous and even stratified in the direction orthogonal to flow. And so as a result, we're much more likely to not see that increase in permeability evolution. I'm going to show you experiments from one more student. Okay, so I'm going to skip this. These are my nice animations, but I am going to skip it. That was this reactive transport simulation of those processes. But what I want to show you is that I had a student who simulated those processes and then simulated the transmissivity evolution. And this is the point I was just making, that in a rock that's typical of a cap rock like the Eagleford Shale, the permeability will increase and then level off because it becomes controlled by these bottlenecks. And that's not what happens in a mineralogically homogeneous rock like the Indiana limestone, which is not a typical rock for capstone. So this is step one in our story about saying that even if CO2 is leaking through fractures in cap rocks, it's not likely to lead to any runaway permeability increase. And another thing we found is that these fractures, when they were reacting, they created a reaction front. So these are mineralogically homogeneous. So the calcite was depleted, leaving behind the silicate minerals. And my student who studied this called this a degraded zone or an altered layer. And then the question we had is, well, if that fracture, if that altered layer is mechanically less strong, then what will happen to it in the context of the pressures that exist deep underground to close that fracture? And so what we did was we partnered with a geomechanics engineering professor at Penn State, that's Derek Ellsworth, and I can turn on these. And what we found is that when you dissolve that calcite in the fracture while also putting pressure and shear stress on it, that altered zone completely degrades and crushes and creates gouge in the fracture. And so the result is this. So this is an XCT image of different amounts of pressure in the normal direction on this fracture. And you can see that that altered zone is completely crushed. And so from a fluid flow standpoint, that material is not going to be any more permeable than the rock and the matrix rock itself. So this is another piece of evidence saying that it's unlikely that this kind of reacted fracture would be a problem in terms of leakage. Okay, I have a couple more slides now on our work where we have looked at the reactions that could create precipitated carbonate minerals that could seal a fracture. One of the reactions we've looked at is reacting magnetite with CO2 acidified brine. This is a reaction that hasn't been studied much because at the pressures at the land surface, this reaction would not be operative, but it could be operative deep underground. So we had the idea of, could we inject nanoparticles and then react them underground? And this is a bit of a teaser. I'm not going to show you results on this because we just did some simple geochemical modeling, not reactive transport modeling. But we are hopeful about that. This slide is my last slide on geologic sequestration before I get to carbon mineralization. And what this is an X-ray CT, or no, not CT, XRF image from the synchrotron, where we're looking at the extent to which precipitated carbonate minerals could seal off a porous medium and inhibit water flow. And so we put bromine in the water so that we were able to color it blue in this XRF image. And you can see that it was not able to get past this middle zone where the carbonate minerals are precipitated. A challenge in this work is that sometimes we don't get carbonate mineral precipitates. Sometimes we get this pore filling calcium silicates that form, and that doesn't that reaction is good in terms of being permeability controlling. It's not good in terms of doing anything with the carbon, though. So anyway, this work has been published, but I won't spend more time on it. I do want to now transition to our other work on carbon mineralization. Let me click. Okay, so the other work we've been doing is on carbon mineralization. And so this is a form of what we call carbon utilization, but it's different from what people normally think about. Our work is different from what people normally think about. We are talking about carbon mineralization, which, by the way, others call mineral carbonation, and I don't think that's a helpful title, so I use the phrase carbon mineralization. We're talking about reacting CO2 with divalent metals to produce sparingly soluble carbonate rocks. But one of the reasons we're thinking about this as carbon utilization is because we're using this process to also help us with another environmental problem, which is to sequester pollution, heavy metal pollutants. So here we are now looking at this image on the right, this nano X-ray microscope, 3D microscope image. And so we're looking at these reactions in the context of water that has other elements in it, particularly toxic heavy metals like arsenic. And that's what's shown here in this image, that when we precipitate calcium carbonate, it takes with it the arsenic. And so it's a killing two birds with one stone kind of technology approach, solving two environmental problems at once. And so let me show you some of our results on this. So the concept, let me start with the concept of carbon mineralization. There are vast quantities of alkaline waste streams that can provide the divalent cations to react with CO2 in the form of they're either metal hydroxides or silicates. An example here is a natural material, wollastonite, and the reaction of these silicates with CO2 is thermodynamically stable, but of course the kinetics of these reactions can be slow, and the precipitation reactions can be tricky. So this is why we are studying them, and an example of how this is tricky is shown here on the left. Sometimes we are able to precipitate calcium carbonate, which is quite insoluble, and sometimes we end up forming vaterite. And vaterite is what you were seeing in those big owl eyes image on the previous slide. Vaterite is a calcium carbonate. It's a polymorph, but it's far more soluble than calcite. So if we want to permanently sequester both the carbon and the heavy metals, then we would prefer to not form vaterite. And that's one of the things we're working on understanding. Okay, let me click. All right, so let me talk to you about this. This reaction is called co-precipitation, where the metals are co-precipitating with the calcium and carbonate. The trace elements, I mean, are co-precipitating. These reactions are also called solid solution reactions because what ends up being formed is a solid solution. And so the solid solution can either be that there is substitution for the cation, in this case calcium, and all these elements shown here on the left of this table, cadmium, lead, barium, strontium, etc., those can also all participate in cation substitution in the calcium carbonate. The one I was talking about in the previous image, arsenic, because arsenic forms an oxyanion, then the substitution that happens is for the carbonate itself. Just a little bit about the approach and the methods. Our experiments are simple, but the analysis is complicated. The experiments are that we have been doing are aqueous phase batch reactions to produce these solids, studying concentrations of trace elements at relevant concentrations to what we might see in environmentally contaminated scenarios. And then we do a lot of analysis, excuse me, analysis of the solid phase using electron microscopy, but also doing a lot of X-ray spectroscopy and other X-ray methods at the synchrotron facilities in the United States. All right, so one of our first experiments was done at what's called the hard X-ray nanoprobe at a National Synchrotron Light Source at Brookhaven National Lab in New York, in the state of New York. And this was not a carbonate. For this experiment, we were studying strontium in barite, barium sulfate. And one of the reasons this experiment is important, and I'm showing it to you today, is because it was our first clue that the uptake of these heavy metals into these simple minerals like barite or calcium carbonate is not a simple problem of a solid solution. And this particle that you see on the right shows zonation in the composition. The strontium does not precipitate with the barite at the beginning. It precipitates later on, probably as it builds up in concentration in the aqueous phase. And so that simple solid solution reaction that I showed you on the previous slide, which itself is not that simple, but it's not the right story. It's not the right way to think about what's happening in these reactions. And here is just one more example. Now I'm showing you a more environmentally relevant pollutant. I'm showing you arsenic taken up in barite. And again, we see a complicated zonation pattern. This was published in Scientific Reports a couple years back. And then we focused on calcium carbonates. Still, our results here are from the hard X-ray nanoprobe. And here we see an interesting story. I have two slides on this. One experiment we did without iron and one we did with iron. And this is the experiment without iron. And in these cases, we don't see that spatial zonation. But what we do see is that these elements are taken up to different degrees, and that is predictable by the radii of these elements and the extent to which they fit into the crystal structure of calcium carbonate. But the more interesting result is what happens when we add iron, as we expect, because in a lot of scenarios there is iron present. So when there's iron, it's quite likely that the iron is not going to be taken up by the calcium carbonate. It's often in oxidized form. And so when iron precipitates, it forms hydroxides. And so it ends up just absorbing onto the surface of these particles. And what is interesting is then that serves as a competing host phase for these trace elements. So for example, you see copper and zinc is really associated with that iron oxyhydroxide phase rather than being taken up in the particle as it was in the previous case where we didn't have iron. Okay, I'm going to skip a little bit just to be able to finish up on time. I'm bringing you back to this question of polymorph. So we've seen this strong effect with arsenic. When arsenic co-precipitates with calcium carbonate, it does promote this change in morphology, and we call this polymorphism. So on the left, you see these rhombic crystals of calcite. As we have more arsenic in solution, we end up with vaterite. Again, that's the owl eyes. And so I just want to show you our exciting results on that, because we have some beautiful images of that. Sorry, I'm skipping a lot. I just want to make sure we have time to finish. But so what you see in this image.
Kathy, we have 10 minutes left for you. Just take your time.
Oh, I was looking at the clock in a different way. Okay,
yeah, we can wait a bit more because it's a fascinating story you're telling. So don't worry if you go beyond. It's really enjoying this. Thank you.
Good. So this image, the two images on the bottom are X-ray fluorescence images. They are hot off the presses. They are brand new from a synchrotron beamline session we had last month. And so here, this TXM image, I call this the owl eyes picture, shows that the arsenic doesn't precipitate in a neat sort of continuum solid solution with the calcium carbonate. The calcium carbonate precipitates, and then the arsenic is taken up later. And so it ends up forming a three-dimensional coating. And I don't want to call it a coating. It's not a coating. It's part of the carbonate structure. It forms this shell. Let's call it a shell on the outside of these spherical vaterite particles. And so we looked at that with TXM, which is this 3D nanotomography approach. And I'm sorry, I realized I didn't put scale bars here, but these particles are about 10 microns. So we're looking at sub-micron scale compositional zonation. And that's what we see if we look again at X-ray fluorescence, where we can look at more particles, not as the resolution is good, but again, we see this arsenic shell that forms. The other thing that's shown in this image that's different is that in this, we're starting to look at multiple heavy metals together. So in this case, we had arsenic and zinc. Arsenic looks green and zinc looks blue. And so we don't find zinc participating with arsenic at all. It does its own thing. And we have these arsenic owl eyes particles, as well as zinc being a separate particle on its own. Just one more thing I want to say about these experiments is that we all know that calcium carbonate is not the most stable, meaning sparingly soluble of the carbonate minerals. And so what we're doing in these experiments is, in addition to forming these precipitates, we are also then exposing them to acid. And so we use hydrochloric acid to expose them to acid. And we want to see what happens to the calcium carbonate as well as what happens to the heavy metals, arsenic and zinc. And what we find is that the calcium carbonate dissolves as we expect. But what we're left with is that the heavy metal is retained. And so that's what's shown in this image here. The arsenic, the calcium arsenate is remaining while the calcium carbonate has gone. And so that is a very positive story for the environmental problem of sequestering heavy metals, meaning that is now, we made a solid phase that we could not have made initially without the calcium carbonate. It's like we needed the calcium carbonate to help us make these solids, and then we got rid of the calcium carbonate. Or that's what would happen, for example, if these materials were exposed to acid. Okay, that was my last slide. So I have the summary and conclusion slide just to remind you that geological reservoirs are essential for greenhouse gas mitigation in the form of negative emissions technologies. Reservoir storage must be secure and viable, and our results have shown that fractures in cap rocks probably will not jeopardize storage security. I didn't today talk about our seismic wave transmission. I have a paper that's not yet published on that topic. And then the third bullet, calcium carbonate minerals can sequester CO2, as we all know, but they also can be thought of as a carbon utilization strategy for solving the environmental problem of taking up toxic heavy metals. That is my summary. Thank you very much for your time. I look forward to your questions.
Thank you very much, Catherine, for this extremely interesting and insightful presentation. We did enjoy and lost the track of time, by the way. If you wouldn't say you were close to finish, we wouldn't notice. So thank you very much. So I'm going to feature some questions so that you could address them as well. I see Yuhong Wang is asking, thank you, Catherine, for this great talk. Is the chemical reaction rate in the lab scalable to the field scale? Or what would you comment on it to make it relevant for the field scale?
That's a very good question. So let us talk. I've talked about several reactions, and the way I'm going to answer your question is to focus on the reactions we're talking about in the last part of my talk. When I introduced that topic, I talked about the fact that there exist millions of tons of these alkaline waste streams from various industry sources, such as fly ash from coal combustion. And everybody's talking about, well, those fly ash wastes that exist as literally mountains of waste from years of accumulation, can't they be used to sequester carbon dioxide? They have an abundance of these metal oxides, calcium, magnesium, iron, etc. Those materials are so weathered often, and when colleagues of mine have used those materials like existing industrial waste, those reactions are not nearly as fast as the ones we study in the laboratory with ideal materials that we purchase from chemical companies. So I'm really glad you brought up this point, because in just about every reaction I've talked about, there's a difference between what we would observe in the laboratory and what we would see in the field, and for various reasons. And so I think that it's a reminder of the caution we need to use in terms of interpreting laboratory findings quantitatively.
Very well. Thank you very much. So we move on to another question by Wilhelmine van Rooyen. She says, thank you very much for the interesting talk. Can we engineer and enhance the mineral trapping now that we understand and characterize it with your experiments? Is it possible to enhance it so we do more secure trapping of CO2 through mineral trapping, which is enhanced in their speed of reactions?
By engineering the composition of CO2. So I like this question. I think the idea of adding additives to the CO2 stream, I think this is what you're talking about, that we would inject underground could be important. When I've asked this question to engineers who are operators of carbon capture processes, carbon transport processes, when I've asked the question about additives like SO2, the reason we've talked about SO2 is could we co-sequester SO2 and CO2? SO2 is an important environmental problem of its own. Could we put them both away underground? And so that's not exactly answering your question, but it's the question of co-injecting. And the answer I got is that the carbon capture processes have to be optimized to produce pure CO2, number one. Number two is anything that might alter the composition to make it corrosive, like if SO2, for example, if we add any SO2 to the CO2 stream and then transport it, any slight amount of water that's present, any moisture, then becomes a very strong acid. Like SO2 is a much stronger acid than CO2. So that was kind of ruled out as a bad idea. So that's let's talk about the other type of additive you might be thinking of. Like, could we be adding these alkaline materials? This is where I think there's some possibility of adding nanoparticles. That was the idea. I had one slide on, and it was the magnetite reaction. Could we be doing that? I think there's some hope to that. Some people are pessimistic about if we add any sort of nanoparticles, then how is it going to be transported through porous media? That's not such an unrealistic thing. People talk about that all the time in groundwater remediation. For environmental problems, we inject iron nanoparticles to provide reactive barriers to clean up groundwater. So I think it's not so far-fetched. And my phone just rang, which it never does. So
that's exactly what should happen in life events.
No one ever uses the phone anymore.
Exactly.
And there it was. Anyway, so that I think there's some promise in the question you're asking, but I don't have enough knowledge. I like the idea of injecting something that would be these alkaline materials. I like that. But then you have to be careful because they react readily with the CO2, and you don't want it to react in the wrong place. So there's a lot of reservoir engineering work that would have to be done to figure that out.
Thank you. Excellent. So the next question is by Sarah, and she's asking about where are we with numerical models to represent what we observe in the lab? And could you please comment on that?
This is a really good point. I don't do this reservoir scale numerical modeling, but I do collaborate with people who do this. And let me just give an example. Mike Celia here at Princeton and I just published a paper with Tom Postma, by the way, who comes from Delft there. Okay, and we were modeling reactor transport in basaltic flood rocks, and so I come from the synchrotron with all these results about all this chemical complexity and surface area complexity, and we're nowhere close to putting that into reactive transport models. It can be done, and I love to collaborate with anyone who wishes to work on that. I think that surface area remains one of the most challenging things. The models that relate permeability to pore structure are always sort of based on simple sandstones that, for example, aren't appropriate in basalts, and yet we don't have better models, so we use them. And here's one more thing that I think is really, really tricky. everyone who does reactive transport modeling uses transition state theory models of the kinetics. So you have a surface area and you have a kinetic part and a thermodynamic part, and you put all that together in your rate equation, and you're good to go. Those three parts, the surface area, the thermodynamic part, and the kinetic part, the two that are really tricky are surface area and the kinetic part. Number one. Number two is that transition state theory equation is a continuum from across the delta G, negative infinity to positive infinity realm, meaning you can use it for dissolution and you can use it for precipitation. And everyone who parameterizes those equations studies dissolution and uses that equation as if precipitation is just the kinetic and thermodynamic reverse of dissolution, and it's not. Mechanistically, precipitation is completely different. And so to think that we can use a model parameterized from dissolution experiments to predict what's going to happen in precipitation, and yet we do it because the math is there for us, and as modelers, I'll say as modelers, we need equations that have parameters and we're good to go. And when we have an equation that doesn't have parameters, we can't use it. So yeah. So anyway, I think that there has to be steps along the way of advancing these reservoir scale numerical models to incorporate these processes.
Excellent. Thank you very much. Move on to another question by Peter Zhu, who says, thanks a lot for the presentation. He's curious about mechanical properties alteration due to the reactive transport of CO2 and beyond the fractures itself, but just the rock itself. Could you comment on that? Just curious, that would the CO2 transport affect material strength properties like tensile or shear modulus of rocks? Or
you are asking me a question on a topic that I have very little knowledge about. I think, but I do think that just the CO2 transport alone would not affect those properties. But what I showed you very briefly is that if there are these reactions where calcite is dissolved from either from a caprock or from a sandstone, it will most definitely change the mechanical properties because, for example, in a lot of sandstones, it's granular with cement, and sometimes this cementing mineral is like a clay, like kaolinite or something, but sometimes a cementing mineral is a carbonate phase. If the cementing mineral is a carbonate phase, then that can most definitely dissolve, and then that would change the mechanical properties.
So I have a very technical question here about how you would possibly reach a steady state in your very small scale type of images in the lab, and it's.
I'm trying to think what images he's referring to.
Reactive, most probably the related to reactions, or maybe the grains, I would say, but it might be that it's
So I'll take this question in the context of the reactive dissolution of fractures. In the laboratory, we end the experiment after days when we have achieved some steady state of the effluent concentration. It's not steady state in terms of the fracture surface. That will continue to
change,
react with fresh acid being supplied.
Okay, very good. So I have two more questions. One is about the impact of heterogeneity. How can we characterize the impact of heterogeneities and uncertainties perhaps on the CO2 reactive transport system, and maybe perhaps translate the physics from core to reservoir scale?
Yeah, this is such a good question because you see in my work, I study mineral heterogeneity at sort of centimeter and below scales. And my colleague here, Mike Celia, who does reservoir scale modeling, he says, why is any of that important? My chemical heterogeneity is important because it provides us with clues to kinetic processes. Like if I look at a particle and I see that there's zonation in terms of like where is the iron, for example, and where are these different elements, that's not because that scale should be put into a reservoir scale model. That's because that information is telling us what reaction is happening first. And by looking at particles on this spatial scale, we're learning the limits of geochemical models, that the existing geochemical models, which tell us that all these reactions are going to happen at the same time and all at the same rate. And that's what we're finding that's not true. So I think one of the exciting horizons for modelers is to think about the reactive transport models in terms of heterogeneity and stochastic reactivity. And the reservoir scale modelers have really been good at thinking about heterogeneity of all sorts of physical processes, like the grain scales and spatial heterogeneities in porosity and permeability zones and all of this. But the next obvious thing is to think in a clever way about how to model all this heterogeneity in chemistry and chemical reactions, and not just treat it using a single equation. So I think that's an important frontier.
Okay, so I'm not going to take all the questions. We don't have time for it, but I'll take the last one from Wilhelmine, who says, she has a second question from you. It says, can this work also, or this methodology to study CO2 related work, help with successfully implementing hydrogen storage in the subsurface? What are the similarities and differences? I guess you would expect that question somehow.
That's really good, Wilhelmine, that you asked this question, that you're thinking this way, because I'm thinking the same way. We spent a lot of time understanding how geochemical reactions can alter permeability in the context of CO2 sequestration, and we've generated a lot of understanding about the extent to which these reactions control hydrology. And I think in hydrogen storage, it's important to understand the potential for sealing up underground spaces. And just as these reactions that I've talked about can create permeability or enhance permeability, they can also inhibit permeability. And so that's, I think, a very interesting direction to think about these reactions and their potential to solving hydrogen storage underground.
Thank you very much, Catherine, for elaborating on these many diverse types of questions, from technical side to philosophical and more vision type of questions. We would count days until we host you at TU Delft in
That's
July.
right.
In school, we hope it will be a sunny day for you, also the period of July, so you would also enjoy your time here. I'd like to also take the chance and introduce our next week's speaker to our audience. Next week, we will host Professor Ilenia Battiato from Stanford University. Ilenia will speak about symbolic scientific computing for multi-scale reactive systems. Until next week, the same time, 4 p.m. European Central, 3 p.m. British time, 7 a.m. California. Stay happy, healthy, and also tuned into our channel for another geoscientific and geoenergetic talk. Thank you very much, Catherine. It was an excellent talk. Thank you.
Thank you, Hadi. Thank you, Marta.
Thank you.